lecture, I'll be discussing neural networks and clustering algorithms. Neural networks are very popular these days as they are flexible and can fit any function. They can be used for both prediction and classification when we are working with labeled datasets. In this slide, you can see a neural network unit named perceptron. Perceptron takes several binary inputs like x1, x2, and x3, and then produces a single binary output. It assigns some weight to each input variable, and then it calculates the weighted average, and if it is larger than its threshold, it returns 1, otherwise it returns 0. The building block of the deep neural network is called the sigmoid neuron. Sigmoid neurons are similar to perceptrons, but they are slightly modified such that the output from the sigmoid neuron is much smoother than the step function output from perceptron. As you can see here, there is an input layer, then weight coefficients, net input function, and then it goes through an activation function. The purpose of an activation function is to add some kind of nonlinear property to the neural network. Without it, the neural network would perform only linear mapping from inputs x to the outputs y. In this slide, you can see a multi-layer perceptron neural network. There is one input layer on the left side, then one hidden layer in the middle, and one output layer. The units in the hidden layer are fully connected to the input layer, and the output layer is fully connected to the hidden layer. Now, if such a network has more than one hidden layer, we can call it a deep neural network. So we are going to work with an example about multi-layer perceptron networks. So we want to train our first multi-layer neural network to classify handwritten digits from the popular Mixed National Institute of Standards and Technology dataset, which is a popular benchmark dataset for machine learning algorithms. This dataset is publicly available, and you can see the link here. I encourage you all to check out this link and learn more about the dataset. Before we discuss the implementation details in Python, I would like to talk about the dataset briefly. The training dataset consists of handwritten digits from 250 different people, 50% high school students, and 50% employees from the Census Bureau. Note that the test dataset contains handwritten digits from different people following the same split. Then the images are stored in byte format, and we will read them into numerical Python arrays that we will use to train and test our multi-layer perceptron implementation. So each pixel is assigned to a variable. Using scikit-learn's new function named fetch_OpenML, it's possible to load the MNIST dataset more conveniently. So technically this function extracts the dataset from this website. So if you click on this website, it directs you to this page, OpenML. So you can find or add data to analyze and etc. So as you can see here, first we need to import fetch_OpenML function, which is under scikit-learn.datasets. Then we import train test split function that we use to randomly split the data into train and test samples. Then we can extract x and y using the fetch_OpenML, and we change the data type of y to integer. So y.astype casts a pandas object to a specified data type, in this case integer. Then we want to normalize x values. Originally, all x values are between 0 and 255. Now, with this line of code, we normalize them, the values between -1 and 1. So x divided by the maximum value minus 0.5 times 2. Now that x and y values are ready, then we can split them using the train test split. And here the test size is 10,000 observations. When we split the data, then we can import multi-layer perceptron classifier, which is defined under sklearn neural network. So we create an object named NN, and then we assign MLP classifier, and we pass some input arguments. Some input arguments are the size of the hidden layer, here 100. Maximum iteration for your neural network, alpha, which is like an error term, and that's why it's very small, and solver, so the optimizer for your neural network. There are some options, and you can see a few comments here. SGD refers to a stochastic gradient descent algorithm. Another option can be ADAM, which refers to a stochastic gradient based optimizer. Another argument is whereboth. So whereboth is Boolean value. It means that whether or not we want to print progress messages. So if you have 10 iterations, you can see 10 messages for each iteration. And the learning rate is the last input argument, which is the learning rate scheduled for weight updates for your neural network. After we create this object, and then we can apply the fit and predict method just like any other classifier algorithms. So we apply fit and we pass x and y from training samples. Then we can predict the values for the test sample, and also we can calculate the score by using the score method. So nn.score, it shows the performance of your training algorithm. You can also apply a score method to your test dataset. Now let's implement this in a Python notebook, and you can see what the result look like. So first we need to import the data. So from sklearn.datasets, we import fetch underline OpenML. We also need to import the train test split function. So from sklearn.model underline selection, import train underline test underline split. So let's run it first. Now we want to extract x and y. X are features or independent variables, and y is our response variable or class labels. So we use fetch underline OpenML function. Then we need to specify which data set we are looking for, which in this example is MNIST underline 784. Version equal to 1. There are different versions available. We also want to have x and y, so return underline x underline y is equal to true. Let's run it. After the data points are assigned to x and y, we do some pre-processing. For example, we want to make sure that y values are integer because y is a Pandas object, so we use y.astype and make it integer. Add a comment here. So astype cast a Pandas object to a specified data set. Data type. Okay, we run it. We can print y values. Okay, you can see it's an array. We can look at its size. So we have 70,000 labels or observations, and it's a one-dimensional array. Now we want to normalize x values, x divided by the maximum value 255 minus 0.5 times 2, then all x's will be between minus 1 and 1. We can print x, and we can also look at its shape. So we have 70,000 rows or observations, and the number of features or independent variables are 784. So each pixel is assigned to a variable, and it shows the pixel values. Now we can split the data in a random fashion. So we define 4 variable x underline train, x underline test, and the same for y variables, y underline train, y underline test. Then we call the train test a split function. We pass x and y. We want the test size to be 10,000. We stratify based on class labels, which is equal to y. Let's run it. Okay. Now we can import MLP multi-layer perceptron classifier from sklearn.neural underline networks. We import MLP classifier. Then we create an object and an MLP classifier. Then we specify some input parameters. For example, hidden underline layer size. Let's say it's equal to 100. Maximum iteration for training your neural network, max underline iteration equal to 10. Alpha, the error term, is a very small number, and you can change it. Solver, we go with a stochastic gradient descent algorithm, SGD. Verbose, we want to see some messages for each iteration, so verbose equal to 10. And also the learning rate is equal to 0.01. Let's run it. Seems that there might be a typo. So hidden underline layer underline size. We're missing an S here, so it's sizes. Let's run it. Okay. Now we can apply the fit and predict methods to our training data set. So we call our object nn.fit, then we pass x train and y train. So it trains your neural network based on this data set. We can also predict the class labels for the test data. So y underline test underline predict is a variable that I define to save the result of the prediction. and the input is x underline test. Okay. So you can see the result for each iteration, and at iteration 10 it stops because that was the maximum iteration, and you can see the output. Now we want to print the training set score and the test set score. So the performance of your neural network. So let's say print training set score is n dot, so we apply the score method to x and y, x training and y training, and y train. We can also print test set score, and then we pass our test samples. So x underline test and y underline test. Let's run it, and here's the result. So the training set score is 0.97 and the test set score is 96%. It means that the model is doing pretty well. Okay. Now let's take a look at some of the images that our MLP classifier struggles with. Here you can see a piece of code. I have already uploaded this code to Canvas. So technically we just want to look at the images which are not predicted correctly. So we are using Matplotlib library as our visualization library. Then we want to look at the images or cases where y-test is not equal to y-test underline predicted value. It means that the actual value is different from the predicted value. Then we create subplots 5 by 5. Here we pass two other arguments, share x and share y. It means that for all graphs we share the same x and y axis. And then you can use the IMShow. The color map is gray, and we can define label and other formatting commands with discussed for creating plots. Now let me run it here. Now here you can see the images. So for example, the first instance, so the true value is 9, but the predicted value was 4. And you can see the similarity. The second instance, the true value was 4, but the predicted value was 6, and so on. So you can see how your classifier is doing and what images were difficult for the classifier to predict properly. So with this example, I wrap up our discussion about neural networks. It can be applied to any other data sets that we discussed in this class, but this example it showed the application for a very popular benchmark dataset. Now we move on to clustering algorithms which go under unsupervised learning. It means that we work with data sets that don't have any labels, so we don't know the target values, and that's why there is no right answer. So for when we are working with unsupervised learning algorithms, we want to find the hidden structure in the data to understand the data or find similarities in points. And this slide, you can see an example. So there are 3 circles, probably show 3 different clusters. So we want to find similarities in data points, and we want to see how many clusters might be meaningful, and if we can interpret clusters based on features or independent variables. Now I want to talk about most commonly used clustering algorithm named k-means. So the goal is to partition an observation into k clusters. So k is predefined, such that each observation belongs to the cluster with the nearest centroid. So the basic goal for k-means clustering is to minimize the sum of a square error within clusters and maximize distance between clusters. As you can see here, there are in this scatter plots, there are three major clusters. Some data points are in between, and that's the goal of the k-means. We want to maximize the distance between clusters, so to make sure that they are distinct. I have listed the main steps for k-means algorithm. So in the first step, it randomly picks k centroid as initial cluster centers, then assign each observation to the nearest centroid, and then move the centroid to the center of the observations that were assigned to it. And then it repeats step 2 and 3 until the cluster assignments do not change or a user-defined tolerance or maximum number of iterations is reached. Another type of clustering techniques is called agglomerative algorithms. So it seeks to build a hierarchy of clusters, as you can see here. What you are seeing here is a bottom-up approach. It means that it allows to create dendrogram to visual clustering, and it creates a distance matrix, and it starts from bottom to up. It means that it adds two values together with lowest distance, and then it goes through all other data points. So for example, in this dendrogram, it first clusters ID underline 0, then ID underline 4. The next step, it adds ID underline 3 to that cluster, and eventually you will see this hierarchy. Now let's discuss two-dimensional dataset and k-means algorithm in an example. We want to create a dataset consisting of 150 randomly generated points that are roughly grouped into 3 regions with higher density, which is visualized via a two-dimensional scatter plot. So we first randomly generate the data and then we visualize them. We show a two-dimensional scatter plot. And as you can see, this is the k-means, so we kind of know they are roughly grouped into 3 regions. For that, we are using one of the data set under sklearn library. So we import make underline blobs. So we want to have x and y variable. Number of samples, we need to pass a few input arguments. So make underline blobs, number of sample equal to 150, number of features 2. So we are dealing with a two-dimensional case. That's why the number of columns or features is 2. Centers equal to 3. Shuffle equal to true. So this is a new statement. Shuffle means that it reorganizes the order of the list items. So we make it true. And the random underline state equal to 0. So random state technically reflects on the number of methods for generating random numbers. So we have plenty of methods, and random underline state is used for initializing the internal random number generator. Here it's equal to 0, you can change it to 1. Then we use the matplot library to visualize the generated data. So we have the scatter plot here, 2 columns. So you can see we present them. The color is white, marker is a circle or O, and we show them. Now that we have the data set, then we can import k-means under sklearn.cluster library. So from sklearn.cluster, we import k-means, and then we create an object based on the k-means. So please pay attention to the input arguments that we are using for k-means. Number of clusters, here we go with 3. You can change it to 2 and see the result. Then maximum iteration, tolerance value, and random state. In the initial, so it chooses the centroid values randomly. When we create our object, then we can apply the fit and predict model. So here, you can see we have a method fit underline predict. Now you can you pass x as input, and then it returns the clusters in your data. And again, here we are not dealing with labeled data, so the input argument as just an x values. Then we want to show the result of our clustering algorithm. Here you can see we are using the scatter method. First, we want to show observations whose class label is equal to 1. So we do that for both columns such that y underline km is equal to 0. We do the same when the class number is equal to 1, so we change the color and also the marker for data points. We have 3 classes, 0, 1, 2. So that's why you see for the first 3 scatter statement. We also want to show the centroid of the cluster. And that's the part that you see km.cluster underline centers method. So for each variable, then it shows the centroid. And we see 3 centroids in the graph. We change the color. We add a label because we want to have the legend. With plt.grid, you will see grid in your plot, and then we can show the result. Now let's implement this in a notebook, and you can see what the result looks like. Okay. So in this part, as I explained before, we import the data set, and then we want to plot it. So let's run this. And you can see the scatter plot of your data set. So we are dealing with a 2-dimensional data, so we have 2 features, 3 centers or clusters, and that becomes our data set. Now we can apply the k-means algorithm. To do that, we first create an object, apply k-means, and then we pass the required input arguments, and then we apply fit underline predict. When we run it, then we want to see the result. We want to visualize the result of the k-mean algorithm. So that's why here we have the scatter plot for all classes plus the center of cluster. So we have 3 clusters, so we expect to see 3 centroids, and for each cluster, which goes through 2 features, as you can see here. So km.cluster underline centers for the first column and for the second column. So if we run it, now this is the result. So first we have a legend, cluster 1, the marker is a square, and the star shows the centroid for each cluster. And then the second clusters are circles, and still you can see the centroid. And then the third cluster, like triangles, and then you see the centroid for this cluster as well. So with this example, we saw how we can apply k-means algorithm to your data set, how we can visualize it for a 2-dimensional data. You can extend it to a 3-dimensional plot and visualize the result. With this, I conclude this lecture.